Hi, my name is Eli Unger, and today I'm going to be doing a presentation about Unicode. So I'm going to focus in this presentation about its development, highlighting the problems it was designed to solve, and I will also talk in depth about the unique mechanisms that it employs to overcome these problems and what makes Unicode, I guess, so special. So Unicode is basically a standard for character encoding. It is intended to unify all the various encoding schemes used by different computers to ensure that a text will appear as intended on all possible devices. The need for a standard in character encoding was long recognized, long before Unicode came along. And one of the first encoding standards was ASCII, ASCII, which stands for the American Standard Code for Information Interchange. However, this standard had severe limitations. It was initially in practice a 7-bit system, which meant that there were only 128 possible binary integers that could be assigned to character values. However, it could also be extended to include 8-bit values as well, and thus there were 255 possible integers available to be assigned to each character, though slots 128 to 255 were in practice left open. These 128 characters were more than enough to handle English, which used the Latin alphabet and had no accented characters. But issues began to arise when American computers started to reach foreign markets. So at that time, different developers managed to get around those limitations by assigning their own characters to the values 128 to 255. And this led to what were called Original Equipment Manufacturer, or OEM, character sets. So as an extension of that, computers designed for the multilingual markets would eventually develop what they called unique code pages assigned to the slots from 128 to 255. And these would allow for multiple languages to be displayed on the same page. For example, you could have a computer intended for the market in the UK, which could display Icelandic and French with all of the different diacritical marks that you couldn't find in just plain ASCII. These numerous variants of ASCII and OEM character sets were eventually codified as the ANSI standard by the American National Standards Institute, but due to the limited space available, some languages with vastly, completely different character sets would remain impossible to display together, for example, Russian and Hebrew. So at the same time in Asia, to tackle the far greater number of characters that you need for East Asian languages, developers had to develop 16-bit systems instead of 8-bit to assign character values. The reason for this was that 16-bit systems have a much greater capacity than 8-bit, in that they allow 65,536 individual binary integers to be assigned to characters. And then at this time, discussions began to crop up regarding unifying the various CJK, or Chinese, Japanese, Korean character sets that began to crop up in Asia at the time. Example of one of these being Japan's JIS character set. The primary issue was that Japan, Korea, China, Vietnam, and Taiwan, they all have very minor stylistic differences in their versions of the same character, as you can see in the image to the right. And so rather than encoding each stylistic variant as an individual character, a debate arose to unify all the variants into one character for the sake of data efficiency. And this proposition was known as Unified Han, or UniHan. The case for UniHan naturally coincided with attempts in America and in the West to standardize existing ASCII formats, and so the idea to create a multilingual character encoding standard was born. This led to the establishment of the Unicode Technical Committee and the Unicode Consortium in 1991 to oversee all future development and extensions to Unicode. So the biggest issue with previous character encoding systems was space, and Unicode tackles this issue in a very clever way. It's not a simple 16-bit or 32-bit system. If it were, it would just double or triple the storage taken up by each character. What makes Unicode different is its capacity for variable width encoding. What this means is that if a character can be encoded in 8 bits, it will only take up 8 bits and can sit in a string alongside characters that are 16. If it were a purely 16-bit system, for example, all characters would be 16 bits minimum, thus taking up a greater amount of storage to display even the most simple and common characters. Unicode achieves this by using what it calls transformation formats. The first of these to be developed was UTF-8, or Unicode Transformation Format 8. In UTF-8, all characters are assigned to a code point, as seen on the right, consisting of U plus hexadecimal value. This code point is used to retrieve the character's corresponding binary data from a menu of sorts, called a reference plane, which I will explain in a moment. The binary value can be between 8 to 32 bits, with the most common characters equal to 8 bits. Unicode was also designed to be backwards compatible with ASCII in that the 128 most common characters worth 1 byte are all equal in value to ASCII's 128. Another transformation format, UTF-16, runs on the same principle, and can actually be more efficient than UTF-8 for displaying some languages whose characters are found in deeper reference planes. That is, sometimes you will be able to encode some characters in 2 bytes where they may take 4 in UTF-8. That being said, for all languages using the Latin script, UTF-8 is generally much more efficient on memory. When a computer reads a text, the only problem is that when a computer reads a text to determine which transformation format to use, it can sometimes get confused, and thus a byte order mark, or BOM, is added to the start of the file. This will let the computer know whether to decode the file as a UTF-8 or UTF-16 format text. So moving on to planes. At the moment, Unicode currently allows for 1,114,112 code points, and these are all stored in what Unicode calls planes, or reference planes. There are 17 of these, and the first of these is referred to as the basic multilingual plane. It contains 65,536 code points, and they are generally the most they're the most common characters that you will find in most of the world's languages. The planes are identified by the first 2 digits in each code point, and thus all of the characters located in the basic multilingual plane, for example, all begin with U plus 00 because it is the very first plane. While in the past, in terms of OEM character sets, while in past OEM character sets had inconsistencies in displaying text on older ASCII-based systems. To avoid a similar issue, Unicode has allocated code points within the planes, which by definition the Unicode consortium will not assign characters to. They did this to allow users to give users space to assign their own individual characters based on their needs, with no worry that they will conflict with existing standard characters in the same position. And then these free use code points are known as private use areas. So just to finish up, I'm going to talk about expanding Unicode and I suppose how it expands. If we look at the plane to the right, this is the second plane, the supplementary multilingual plane. And what's important to note is the large amount of code points that are yet to be assigned, all of the ones in white. So Unicode is designed to be future-proof in that while there are 1,140,112 code points available, the vast majority of these are still unassigned. And realistically, given the amount of characters in world languages, they will not realistically ever all be filled. Characters are constantly being added, however, and one of the biggest and I suppose most well-known additions was in 2007 when Google requested the Unicode consortium to add emojis, which they were eventually added in Unicode 5.2. What is interesting as well is that anyone can actually submit a character to be added to Unicode as long as they meet a list of requirements that are on the Unicode website, such as the character not being suggested before and it not just being a stylistic variation of an existing character in Unicode. But yeah, so I'd like to end my presentation here, but thank you very much for listening, and I hope this explained Unicode just a little bit better. The next slide will have all my sources. Thank you very much.